using the room microphone with.
Okay, do you hear me now?
Coming through.
Okay. Ooh, I can't stand hearing myself. Now I've got to find. Okay, for some reason now this is working. I don't understand. Okay, so so the outline is as follows. I'm going to start with a little bit of a motivation why we're studying this thing, and it's just. I mean, we've been studying this a long time, and the whole series, not just because Joe Thompson told us to do it, but it's really in the ultra clean limit. And so we, using CeColn5, we were able to really promote our, or just understand and start using the point contact spectroscopy where you need a really clean sample. It does have a neat X squared minus Y squared pairing symmetry, and that's always kind of fun. We don't know what the pairing mechanism is. We have some thoughts. They're mostly back of the envelope concepts of an idea, but one of the reasons I'm happy I'm early in the week is number one, I get stopped fretting about the talk after about an hour, and number two, if you guys have any ideas, I would love to discuss it with you and pursue it, because I am not a theorist. So what we did, and for these particular studies, we've looked at a bunch of different materials, but I'm just going to focus on this one right now because I think there might be a horsey in here somewhere. So the tunneling spectroscopy of high quality junctions, planar tunneling, as in 3 crystallographic orientations over a range of temperatures and the magnetic field up to 18 Tesla. And I'm going to spend a little bit of time on the junction fabrication to show you the kind of diagnostics we do to have some idea that what we're measuring is intrinsic to the material, and it's very reproducible. So we were on this must be preformed pairs for a while. There's like a pseudo gap in this material. And I'm kind of convincing myself that the STM people were calling it pseudo gap, a precursor of a gap. And I'm wondering if it isn't like the pseudo gap and height. I'm just going to talk now so you can think about it. So, you know, in the Coop rates, we sort of, for many, many years ago, we know the pseudo gap in the Coop rates is pretty complex. And there are places like what Ong had done a while ago using nurse effect, that certain areas in the pseudo gap seem to be exhibiting preformed pairs. And several materials, like some of the iron-based superconductors, there's a lot of evidence for preformed pairs. And I don't think that's a weird idea anymore. I did when I was younger. We don't know yet. Is it a pseudo gap, preformed pairs, condo hybridization? Probably all of the above. It's a pretty complex system. And I'm going to show you a couple of just one slide of each. There's a lot of STM measurements out there, and there's a recent pressure-dependent PCS that argues that it's all hybridization. And there's a shock noise spectroscopy that's very cool that argues that it's preformed pairs. Okay, so I think the take home is that we have the TC, which is 2.3 degrees, and about twice the TC, we have something else going on, which is like a pseudo gap or preformed pairs, or who knows what it is. And then what we find in our tunneling, that below twice TC and below TC, we see a certain field effect that grows linear with temperature. And when we're above that temperature, we don't see it. So that's the take home thing. We see a field induced splitting that it goes up to very high field that's linear in field, as long as you're below this 2 times TC, whatever that is. The results are consistent with Cooper pairing due to local moment F-level scattering, which is Rebecca Flint and Pierce Coleman theory from a while ago. They don't buy it, but I'm going to talk about it anyhow.
We don't buy it.
Help me understand it. Okay. I didn't think you bought it. Okay, so most of you know what serum cobalt-5 is. If not, it's a really nice material. TC is pretty high for a heavy fermion, 2.3 degrees, which makes it easy for me because I go to helium-3 but not Dilfridge typically. It's of course non-fermi liquid above TC. I have this theory which I'm always proposing all the time, which is what gives you, I have to say it. The definition of an unconventional superconductor is that above TC, you do not have a Fermi liquid. So the reason I started that way, when the iron-based superconductors were discovered and people are accepting that it's, S plus S minus in the pairing symmetry, that's the same symmetry as the underlying lattice. Some of you may remember the definition of an unconventional superconductor was that the pairing symmetry of the order parameter was a lower symmetry than the underlying lattice, right? That's not true with the iron-based superconductors. And so I've been studying this for a little bit longer than 2 years. I think this may be my swan song physics stuff. That what happens is that you break the quasi-particle, whatever they are, fluid above TC, right? Whether you have some heavy electrons, whether you have pneumaticity, whether you have quantum phase transition, all of a sudden, your electron fluid is not showing you what the lattice is, right? All of a sudden, the electronic fluid, the optical, transport, thermodynamic properties are non-Fermi liquid, right? And a Fermi liquid, from my standpoint as an experimentalist, is that you can take the atoms, what's in there, and where they sit, and you can calculate all those properties. The electronic, thermodynamic, and transport properties. And as soon as you get into any of these materials, when you go above TC, you can't do that anymore. There are some successes, but it's not, we don't have a Fermi liquid theory, probably because there's probably 50 different theories out there. Like I said, pneumaticity, pseudo gap, quasi, quantum critical transitions, et cetera, et cetera. So I think that's really interesting and fun. And so one of my take homes that I've been doing is the superconductivity since I didn't get my PhD in superconductivity, but since I've been a postdoc, is that I don't believe for a second there's one theory of all this stuff. This is why it's so much fun. We have like 40 or 50 unsolved problems, and I think it's harder than the Higgs boson or gravity waves, but that's my own. It's because I love it. Okay. So what we have is, I'm not even sure this curve is completely understood. This curve here is the resistivity versus temperature. And, it looks like at higher temperature. Oh, sorry. It looks like at a higher temperature, it looks like a regular metal. And then you get it coming up. This is really cannot be explained as a single impurity condo. But what we do have once we get up here is that we get some condo hybridization. And I think we pretty much understand in a general why this happens. So the resistance starts to go down because you're using up all the itinerant electrons by scattering from this condo lattice. And then the condo lattice gets compensated, right? And then it acts like a Fermi liquid at low temperature because it don't, the next itinerant electrons at lower temperature don't see these scattering centers. And then at about 2.3 degrees, so it's way down there, it actually goes to, it actually superconducts. And there's some argument that why does susceptibility doesn't happen at the very same temperature as TC. Here's the specific heat. It's pretty heavy. And the specific heat argues that the heavy electrons are what forms the Cooper pairs. Now here's just another little bit of an introduction. Oh yeah, hello.
Hello, sorry, I don't really know very much about this material.
Good.
Can I just briefly ask you, so you said it's got a pseudo gap phase, right? Like the cuprates. So, okay. In the cuprates, you have these copper oxide plates which drive the superconductivity. In this material, does it have, is there some sort of like the indium, sorry, I'm just looking at the structure, indium cobalt, is it like this?
Yeah, so the question was, you have the pseudo gap phase and the cuprates, there's also a pseudo gap phase. Is it driven by the superconducting layers? This is a layered superconductor, it's highly anisotropic. To answer, is the pseudo gap driven by the 2D behavior? I don't know the answer to that. Okay, I think it's a great question. But one of the things why this was also interesting is many of the properties, like when I tell you about the point contact that just came out about a year ago, that was done by Tucson Park and my old student, Xin Lu, and some other people, it really does. And in some of the STM works, they say it really looks a lot like a cuprate. So that's all I'll tell you.
Other structural transitions. So like in the cube race, you have these structural transitions.
Yeah.
When you go to the low temperature phase, that's where the superconductor links with where the superconductor. In this material, you get
The structural so that's a really good question, because for several years in the early, the question is does anything correspond to a structural transition? And in the coupe rates for many, many years, it was a red herring, because we knew there was this structural tipping transition that happened in low temperature, and we were able to determine it had nothing to do with the superconductivity. So typically, I think in general, structural transitions are often not associated with TC in many materials. The superconducting transition is typically second order. Unless you're in a magnetic field, then you can be second order. You can be first order, sorry. Okay, good questions. Thank you. Okay. And if I'm saying anything wrong or not clear, I really like to be interrupted. It's in my DNA. So feel free to do that. Okay, so here's a couple of pictures here. And when I spent I had a long flight going Tallahassee, Atlanta, and then back to and then here, and you get here early in the morning and you have a lot of time to wait before you can check into your hotel. So I spent a lot of the last week rereading the old papers. So what do we have on the left here? In the left, I seem to have lost it. Oh no, it's from this was 2017. But there were several thermal conductivity papers and several other papers that showed it was D wave. This is just a heat transport that if you do it as a function of angle, you see the oscillations. But what we were able to do by point contact a few years ago was show that in fact it's dx squared minus y squared. And that's because tunneling is more of a spectroscopic measurement. You can, in planar tunneling, you have something called the tunneling cone effect. So the electrons really come in at a pretty low angle if you have a good junction. So you can see the difference between the different crystallographic orientations. That's also true if you have a very smooth and clean junction for point contact spectroscopy. So without giving a lecture on what point contact or Andreev reflection spectroscopy is, what we did on the right here a few years ago, it looks like 2008, is that here's just a couple of examples, is if you do Andreev reflection in the C-axis or the 110 direction, and this was years of work of making sure we had reproducibility, et cetera, et cetera. The shape of those curves tell you where the node is. So do any of you know what the BTK theory is? Blonder, Tinkham, Klatwick? Anybody want a quick 10-second explanation?
Yes.
Okay, good. So, so we know what, I have to do these kind of lectures. We know what the Schrodinger equation is, right? That tells you what an electron does. We love the Schrodinger equation. One time I said Schrodinger and someone in the audience just beat me up over it. It's gap. Okay. And then we have in superconductivity, these equations called the Bogoliubov-de Gennes equations, right? So it's two Schrodinger equations. One's for the electrons, one's for the hole, and there's a cross term. Okay, and then you fit to it, but it's really hard. So BTK makes an approximation. It's called the Andreev approximation, and it's basically saying things don't happen too quickly. So I forget what the exact definition is. It's something that's also something called quasi-classical theory. So it's just looking at the local effects and you're not trying to do the calculation of the entire system. So you're just applying quantum mechanics to a local area, and it works pretty well. So what you do is you have these equations that you just fit the curves to. And you have the tunneling limit where you get something. I should do that. I didn't realize it was a school. I should have prepared this. So you know what I'll show you what a tunnel junction is, right? You know, it basically looks like this for an S-wave material. And when you have the Andreev reflection, what happens is it's a very understood, not surprising phenomenon. You shoot an electron into a superconductor and it retroreflects a hole, which means if you send one electron in, what you measure is basically 2 electrons out, right? A retroreflected hole looks like an electron, et cetera, et cetera. So you typically get twice the conductance. So what we're seeing, since there's zoom here, I don't know if they can see the pointer or not. That's why I have this fancy pointer. But what we see here, we spent a lot of time analyzing this, but that increase in the conductance and the flat top, and sometimes it goes down a little, we can fit that very well to say that is a lobe direction in the order parameter. And if we look at the one on the right, I spent a lot of my adult life studying this stuff, that we're injecting electrons into the nodal, the 110 direction. And basically, we understand that. If you want an explanation that's not quite right, but will satisfy you, you know, phenomenologically, is that the one on the left, if you imagine going into the 100,010, it looks like a S-wave superconductor. If you're going in the 110, you see that it goes down in a point, and that's what you measure. You can actually do that mathematically. Okay? So any other questions, please bring them up. So then we started. So I wanted to say that this is running ahead of me, but I wanted to say that we started studying this, and then it became very, very popular. And you can see, I don't have all of the STM measured, but this became very, very popular to study, there's a pseudo gap, and this is mostly from Milan Allen's group. More recently, it's Allen's group, but historically, Yazdani and Davis, of course. And what they found is over and over again that they see pseudo gaps. What they mean by pseudo gaps, if anybody's looked at the old Dijon, you know, pre whatever you call it, when it looks like you're going to start pairing just above TC, you can see that. You can see that sometimes, but they're seeing like 1.2 times, and now we're seeing twice TC. You see something that shouldn't be there. If it was a conventional superconductor above TC, it should look fairly liquid-like. But they're seeing some kind of gapping that's going on up there. And whether it's gapping or some other effect, I think is still up for discussion. So you can see that I think this one by Guinness et al. Was really interesting because they go in sideways, and depending on the layer, they see something that looks like a hybridization gap or preformed pairs, depending on where you are. And these are all too complicated for me, but basically all these STM experiments are very intriguing, and they show not as a function of temperature, but as a function of higher and higher field, that something is occurring above HC2. Yeah.
Laura, is nodal structure also evident in just tunneling spectroscopy or not?
Yeah,
It is. So this is consistent with that.
this is, yeah, I'll show you some tunneling, because that's actually what I have here, because PCS is harder to analyze and harder to diagnose. And so now that we have the regular planar tunneling, but the planar tunneling in the STM does show at least the general D wave shape, but it's harder to show the orientational because it's hard to cut in. But in planar tunneling, that, you know, there's advantages to planar tunneling. One is you can,
But it's consistent.
it's consistent, yeah. Yeah, there's no doubt now. We finally, you can have 3 or 4 different condensed matter physicists agree on something once in a while. This is one of those things. So yeah. So and this is, yeah, so you have perfect leading question. So what we do, this is not STM. And there are advantages to this because this is what I know. So this is what I do. That's the main advantage. But it's not simple. So basically what you do is this is just sort of general. What you do is you have a material, you put an insulator through it, and then you have another material. And you measure the resistance drop across that tunnel barrier. Whereas in a classical system, you don't get a resistance drop. In tunneling, everything is spread out in space and time and energy. So you actually get a wave function that gets through. So up on the upper left is what we're saying in practice. That's what you have here. You do IV dVdi, which is the dynamic resistance. What I don't have data for right now, but we have some preliminary data we showed at the March meetings. We do have the second harmonic d squared I by dv squared, which gives you a lot more resolution and a lot more sensitivity. We're actually applying that to some hexaploid right now, but anyhow. So the middle picture is, again, this is the standard semiconductor picture of tunneling, which is you put this voltage across it. You can put a voltage across it because you got an insulator in the middle. So on the left side is the Fermi liquid. On the right side is supposed to be a comic book representation of a superconductor where you have a gap in the density states around the Fermi level, and to pile up the density of states at the gap edge. And that's exactly what you measure. So this is on the upper right is another, I can't remember if that's our data or a cartoon version, but you can actually get data that look that good at low temperature. So that could be any simple S-wave superconductor where we see at zero bias, we don't have any electrons get across because everything's paired. And that's going to happen until you get to the gap edge. And then Mr. Fermi told us that you have a peak in the density of state, so all the electrons, high probability tunneling through. By the way, I was an undergraduate when I learned the Fermi-Golden's rule in quantum mechanics. Everything I've done in physics relates to Fermi's golden rule. So it's all spectroscopy, optical or whatever. So what we have on the bottom here, as long as I'm taking a second on here, and because there's a lot of students here, what we have on the bottom here is data from our laboratory. And that's what we have. I make all my students do this just to practice. And this was very nice because it's 1.7 degrees. And what we have here is lead tunneling. At this temperature, the aluminum isn't superconducting, the lead is. If you're at a lower temperature, things are a little sharper. This isn't SIS, this is NIS tunneling. Aluminum's normal. And we've seen nice sharp density states peaks. It's not a perfect flat bottom. We kind of understand why, but what's important are those little arrows there that show those bumps. This is what proved the BCS electron phonon theory of superconductivity, right? So what's happening here is that in conventional metallic S-wave superconductors, most of the periodic table we think, it's electron phonon mediated. I don't think I have to explain this here. So what happens when you're down at low temperature and you go superconducting and then you go tunneling from the superconductor to the normal metal, the tunneling electrons that get through actually feel they're at low temperatures, so they feel that phonon. Okay, you can actually, this is called the L.A. function. You can calculate it, we understand it. And by the way, I just realized that the definition, we were on that paper with Nigel about the definition of, that was classic paper, fantastic. It's in the Ginsburg series about unconventional superconductors, fantastic. So this actually helped us understand strong coupling superconductivity. But what's important to remember through this talk is that if you measure neutrons, and by the way, these 6 and 8 millielectron volt phonons were measured in neutrons. And then they saw them in the tunneling. And Macmillan was able to go back and forth and say, oh, these are part, and they only show up when it's superconducting and do some other calculations. So if you have excitations that you could measure with neutron scattering in other ways, whether it's spin or whatever, phonons, you should see it in the tunneling if it's part of the mechanism. And if you really don't, then you go to higher resolution, you make better jug, et cetera, et cetera. But then if you still don't see it, then you still go to higher resolution, But at some point you just kind of give up. And so one of the points I'm showing this is because there's a famous neutron peak in the steering cobalt-2 V5 that no one's ever seen in the tunneling, right? That's a spin-spin correlation one that's seen, as you discovered, in the cuprates, and it's also in the iron base. So, yeah.
A quick question. So you explained earlier what Andreev process was. The reason you don't see here any Andreev peak at zero bias is that because the aluminum oxygen waves with thick.
Yeah, exactly. Perfect. So Andrea asked the question, why don't we see an Andreev peak here? So in the BTK theory, and we've done a bazillion junctions, if you have a very, very high transmittance junction, then you see the Andreev peak. If you have a low transmittance junction, like a thick barrier, then you don't see an Andreev peak. The problem of Andreev reflection goes down quite a bit. It's right there in the theory. And so you go from point contact to tunneling, for instance. You go from Andreev reflection to tunneling, depending on the transparency. One of the cool things about BTK was I was always trying to measure, just the background. And the interest, so when I was a kid, we didn't understand proximity effect. And now we kind of understand it as all Andreev reflection. And so what happens if you have two materials that have a very different mass intrinsically, so you have a very different Fermi momentum, that decreases the chance of tunneling. It decreases the chance of Andreev reflection. You have an electron going from a low density a low momentum, fermion momentum material to a high fermion momentum material, and it doesn't Andreev reflect. It bounces back. What's the explanation, the physical explanation? It's shining light into diamond, right? The mismatch, the Fermi momentum mismatch is so high, it doesn't Andreev reflect. So one thing that you do put in these equations is, even though you have an Andreev, why is it not so strong? It's because of the mismatch of the Fermi momenta.
So in case you see two peaks, I mean, why is that? I mean, typically, you saw, in this associated with gas, right? But then you have two gaps, so in this case.
I'm sorry, are you asking,
Yes.
so the answer, what are the kinks? Are you asking about
Yeah.
these two?
Yeah.
These are phonons.
I know, but typically, I mean, it's just a mode electron coupling, right? That's typically associated with.
Exactly,
Yeah, but why do you have two? That's my question.
because lead just happens to have a 6 and an 8 millivolt
Also, the two gaps in
phonons.
that.
Yeah, there's two phonon modes, so these are just these aren't superconducting, these are just the phonon modes. So, yeah, okay. These are great questions, thank you. Okay, moving right along. So just to tell you more about the sample processing. So if you can grow thin films of the material, that's what we prefer, you get a better surface. If you don't, so we do have thin films of samarium hexaboride now that are really good, but we don't have them in CeColn5. So we get these really great materials. We've gotten some from Zach Fisk and Ryan more recently. And then that's how they're grown, traveling solvent float zone method, and you polish like crazy. It could take you a few days to I mean, we have like a lot of reports, internal reports, and mentioned in papers on how we can polish these. I'll give you some numbers, how flat they are later. And then when you're done, you have to, you've done polishing the CeColn5, then in the vacuum system, you etch off any impurities in the surface just by ion etching. And then you put a little bit of aluminum on the surface. And within the vacuum system, you do something called plasma oxidation, which I've worked at for many, many years. Instead of just oxidizing in air, you just give it a little oxygen and put on a little plasma in a little ring thing. And what you do is it creates species for the oxygen, and they just have no trouble going right in. So you could actually, we learned this in the high TC thing, that you could actually, get oxygen into a bulk cuprate easily through this plasma oxidation. High pressure oxidation squeezes things down, so it's hard to get the oxygen in. So this is kind of nice because you have all these nice species. It makes it really clean. And then we very quickly deposit a lead counter electrode. And so here's the schematic that the counter electrode is lead, tunnel barrier is aluminum oxide, CeColn5 is the bottom. I'm going to say right now is that I have some preliminary data in my backup slides, but because of so many questions in the data, we're developing using different counter electrodes and different barriers. So we've developed the magnesium oxide barrier just to see what's going on here. And you'll understand why later on, because one of the explanations for what we see is an impurity in the barrier. Okay, this is a lesson for people that don't like planar tunneling or anything. STL is a good way to do it. There's all sorts of good ways, but you have to use diagnostics. Okay, the best diagnostic for a new material is use your counter electrode of something you understand. I just showed you we really understand what the superconducting tunneling density of states of lead looks like. We know how to fit it. That tells us exactly how good the junction is. How good the junction is if you do the fitting, you can look at it and kind of tell if you're doing it for a while, what percentage of the electrons get across that junction through single step elastic tunneling, not taking multiple steps, not shorts, et cetera, okay? So what you do is you go down to low temperature, low field, you look at the tunneling. If the lead looks really good, like that classic case that I showed you in the previous slide, then you drive the lead normal. You do it by either putting on, in high TC, you take data at 10 degrees instead of 4 degrees, right? High TC doesn't care. Here you put a kilogauss, 2 kilogauss on it. And these, as Malta said, have very, very high HC2s. So it doesn't care, it doesn't change the junction very much. Now, the second one is once you have reproducible tunneling characteristics and you understand what it looks like, then you can change the counter electrode material. Because once you understand what the density of states of like cerium cobalt indium 5 is, and you want to use a silver counter electrode, we know what a good junction on cerium cobalt 5 looks like. So the tunneling density of states of the new material becomes just as good as diagnostic as the lead tunneling. So these are important diagnostics that you can do. So here we go. So we're starting out, so here's this surface, the surface roughness is, I'm sorry, those are in angstroms, I should have gone into, but the roughness is, I think it's, about 1 to 1.5 nanometers. So it's very smooth, there's some details. So what do we have here? This is low temperature, zero applied field. So we have SIS tunneling, cerium cobalt indium 5 superconducting, insulator, lead superconducting. And for those of you, what we do know is that you see when you have SIS tunneling, two things are nice, is that you get very, very sharp characteristics. Because if you think about that picture I showed you with the fermion liquid and the superconduction density states on the other side, if you can think about convolution, some of your math people, if you have a superconductor on both sides, you have these sharp density states that are mapping each other out. So it's really sharp. The other thing that you see, and it's easy to do this on paper, but what you get when SIS junction is you get delta 1 plus delta 2 and delta 1 minus delta 2. I can draw the picture, you can take my word for it. So what do we see here? Here we're at 20 millikelvin, so everything's superconducting. SIS junction, and lead bonons are clean and clear. So that's good junction. The center is nice and flat, like you would expect for lead as an S-wave superconductor. But we also see the lead gap and the lead plus, we see delta and delta 1 plus delta 2. So why don't we see delta 1 minus delta 2? We understand that. It's because the cerium cobalt indium 5 doesn't go to 0. So again, you can do this with sliding pieces of paper. But what this tells us is that this is a really good junction. Okay, very clean. Almost everything's getting through a single step elastic tunneling.
Question,
I could tell you in the question.
just a clarification, delta 2 for 115 would be the maximum gap,
The what?
but for cerium cobalt indium 5,
Yeah.
since it's D-wave,
Yeah.
it would be the maximum gap.
I think, since the question was for cerium cobalt indium 5, would we see for delta 1 plus delta 2 the maximum gap?
Obviously.
And I think what we're looking at here is the 001 direction. And so you basically are picking up the maximum gap in that direction. So good question, thank you. Okay, so then what do? Remember, these are like 8 and 11, 8 Tesla for HC2. So we put a little bit of field on it. Okay, we typically use 2 kilogauss to make sure we don't have any residual. Lead superconducting, and the cerium cobalt indium 5 doesn't give a hoot, right? So what do we have here? So this is, we've driven the lead normal. So it's low temperature. We've driven the lead normal with 2 kilogauss. And now we're only looking at the tunneling conductance in the 3 different crystallographic orientations. So the top one is 001, but the red lines are the BTK fit. So, fits are always a little bit sharper. You can see on the top one, the fit is a little bit sharper. There's some scattering in there. You can also see the reason why you don't see a delta 1 minus delta 2 is because you can see there's still a lot of conductance left in the central gap at zero bias. And that's pretty typical with a D-wave superconductor. I think they call it non-local effects. So if you're tunneling into almost any direction, you're gonna I don't know if you guys understand all this, but if you're tunneling into the 110 direction, you just break pairs like crazy. And I can go over that if you want. But there's always reflections that break pairs, and that kind of just fills up the gap. I could go into that if you want, but maybe you won't, but maybe you'd like that. There's the 001 direction, the 110 direction, it fits really nicely. And we see that is what you expect for D-wave superconductor when we fit it. It looks like a pretty good junction from these parameters tell you pretty much the quality of the junction. It's a pretty good junction. The bottom right, we don't completely understand. Okay? Typically for a D-wave superconductor, this is what you expect for a D-wave superconductor, a peak in the center. Does anybody understand that? No. Okay.
What's the difference between the middle and the bottom? Explain.
So these are just three different crystallographic orientations. Okay, so the top one is going into the C axis. The middle one is going to the A axis. And the bottom one is going to the square root of A squared minus B squared axis, or plus whatever direction. Yeah. Okay, so you expect a peak, like I showed you in the reflectivity, I can tell, maybe I should have given more of I thought I was gonna have all experts here. You actually do expect a peak in the tunneling density states in the 110 direction. That is a measure of the sign change of the order parameter. Anybody want a quicker explanation of that? Okay, so, yeah, okay, so Anderson, sorry, maybe I will need the time. You were right, you were 100% right.
You need all the time, yeah.
Yeah, I thought I didn't have anything to say, but there's a lot of history here. Okay, so remember we talked about Andrew reflection as you send an electron into, let's assume there's not any momentum difference or anything. You just send an electron and two electrons come out. And the proximity effect is that if you look at the probability of finding Cooper pairs in the superconducting side and the normal side, okay, if you're into the normal metal, you're not going to find Cooper pairs. If you're in the bulk of the superconductor, you find Cooper pairs. In between, there's a drop off. Okay, that's the proximity effect. When you put niobium next to copper, you lose a little superconductivity, TC goes down, the probability of finding is well understood that that's the proximity effect. We used to think of it as Cooper pairs kind of leaking between the superconducting and normal metal, but that doesn't make any sense, right? This is a complicated many-body problem. What's actually going on is that it's an Andreev reflection. The electron goes into the superconductor, and the superconductor says, I can't have anything on my Fermi surface. I'm not going to let you in here. So it ejects a hole. Okay. And so what it does is that electron that goes in picks up a little coherence from the bulk of the superconductor and brings it back out. So the electron coming in and the hole that's retroreflected feel some of this coherence. And inside, within about a coherence length of the superconductor, where it's trying to get all these, exchange these electrons for a hole, where you are suffering in the superconductivity, you have reduced the superconductivity in there. So the microscopic explanation of the superconducting proximity effect is Andreev reflection. Backing up a little bit, we see Andreev reflection breaks pairs. Right? And if you have a very, very strong Andreev reflection, you strongly break pairs. I should have more stuff written here. Anybody want to stop me?
So just to conclude, so the bottom one, the 110, there you see Andreev reflection. So maybe it's a stupid question, but why don't you see it in the other two directions, different junctions?
If you tunnel into, so the explanation is this. When you if you have the surface of a 110 superconductor and you have electrons bounce off of that surface, the electron, if it's 110, starts out going in a plus order parameter direction, reflects and sees a minus order parameter. And the Cooper pairs go, that's a very, very strong Andreev reflection. I'm going to break pairs. So in the high TC superconductors, if you tunnel into the 110 direction, you have quasi-particles along the surface. And you measure that within the superconducting gap as a peak in the density states at zero bias. Okay, so what we have here is a peak at the density of states zero bias that's consistent with being what what these are Andrea bound states, so they're well understood. One of the problems we can't say for sure is because this is larger than the gap. And we have not been able to fit it completely, although if you see that little splitting at the top at 2 kilograms, that's an indication that it's an Andrea bound state. So it's consistent, I mean, it's not surprising, it's consistent with D-wave.
But don't you expect to also CeColn5 speed to Andrea, the other cuts?
No, no, you don't, because if you're going into the 100 state, you're going into the lobe. And as far as the C-axis, you primarily pick up the lobe directions. To really pick up these clean Andrea bound states, you have to be near 110. You don't have to be exactly at 110, you have some leeway, but you have to be near 110 to break those pairs. Yes.
If you made your junction, your insulating junction thicker and thicker, how would the bottom curve change? Would it just get smaller? This?
Yeah, I think if you get it thicker and thicker, if you fit it correctly, you'll do things like changing, you'll pretty much see the same gap. You'll pretty much see not anything different until you don't tunnel anymore. So the dips and the peaks are intrinsic to the material and not depend on the barrier. Unless you go into the unless you go to the Andrea deflection limit, you're gonna see something different.
So making it thicker, the double peak at the very top wouldn't change.
No, I don't think it would change. What you would see then, you think like these curves sitting like Z, that would increase. Z is a barrier strength.
Question about the zeros at the Z-axis.
Sure.
The BTK fix shows a V shape, but the data shows a U shape.
Yeah,
Is that because of form factors? Or-
that's just due to some scattering in the material. I think so. The question was, the BTK fit shows the V shape, the data show the U shape. Why is that? And I think that's because when you think about what's going on here, you start getting some scattering and we don't really have a good explanation, except, yeah,
You think about it as a filled in V shape or?
yeah, kind of.
Yeah, okay.
Question, as you know, in cuprates, as a function of temperature, the gap doesn't really close, it just fills in. Is that similar here, or is it as a function of
It
temperature?
depends if you're measuring the pseudo gap or the TC gap. If you're actually measuring the gap so the question was, in the cuprates, does the gap fill in or change with temperature? It actually does change with temperature. So it was clouded for a long time, is that I was trying to figure out why this. If I was as smart as John Franquat, I would have discovered the pseudo gap. But I'm doing this tunneling, I'm trying to figure out why is this just filling in? Is that you're always measuring the pseudo gap, and inside you can learn to differentiate between those. So. Okay. Temperature dependence. Okay, so here we have the next couple of slides are only the temperature dependence of these junctions. And so what we have on the top one is a 001, the 100, and the bottom one is 110. And what you can see is that we're looking at the superconducting gap. Okay, it's depending on the junction, it's more smeared out or less smeared out, but we definitely see a gap in the center. That's due to the superconductivity in the top two. And as you raise the temperature, when you go above TC, you still see something. Okay, so one of the ways you can see it is looking at the color plot on the right side. The color plot on the right side, I hate color plots, but it helps you get published. The color plot on the right side is just telling you the dotted line, that white dotted line, temperature is going up in each of those plots. The white dotted line is where TC is. So the take home message here is that we don't have an explanation, but unlike a simple conventional superconductor, stuff's going on above TC in all three crystallographic orientations. Okay, so that's the takeaway, and that's what we're going to do here. And then I want to just point out we have some data here, so we just plotted it up. Basically, I'm saying that again. And like I said, the STM called the precursor, and all the STM work was a function of field. So we're showing that, hey, we agree with you also in temperature. Besides you having these precursor states that you measure in STM as a function of field above too high of a field, here above TC, we're seeing something that's a precursor state. Now we go to the
Can I
magnet.
just ask, if you
Sure.
read those color plots for a conventional superconductor?
Yeah.
You wouldn't see anything above TC.
Correct.
Okay, just.
And again, so the question was, in a conventional superconductor, you wouldn't say anything above TC. That's the definition of a conventional superconductor. You've got a nice little Fermi liquid. And Walter Harrison told us years ago that if you're planar tunneling into a Fermi liquid, you never see anything. You always get a flat conductance, which is fantastic, right? The reason why, and Walter Harrison, Harrison's theorem from the 60s was saying, why should you see anything at all, even in a superconductor? Okay, so if you're tunneling into a Fermi liquid, if you remember the tunneling equation, you have the density of states multiplying the Fermi velocity, and the Fermi liquid, you have dE by dk multiplying dk by dE. So you should see nothing. So there are all these papers that came out that said, why do we see a tunneling density of states? Why do we see this super quasi-particle density of states change below TC? Why do we see this gap? And the answer is the superconductor is not a Fermi liquid. So that standard tunneling equation, it doesn't fit, right? So that's sort of cool. It's a nice definition. It helps us understand it.
Yeah, what about D wave above TC? Is there any conventional D wave?
No.
Okay,
So the question is, what about D wave above TC? So I have this public lecture that I give, which I'm sure some of you are like sick of it by now. But it's called the dark energy of quantum materials. I was, trying to play this game and it was kind of fun, but basically, again, I classify an unconventional superconductor as a non-Fermi liquid above TC. That's only my definition. So if it's a non-Fermi liquid and you're tunneling between a Fermi liquid and a non-Fermi liquid, you're gonna see something. So for instance, in the iron-based superconductors, we could map out where the magneticity live, right? In the cuprates, we certainly can see, the pseudo gap. We don't know what it is, but we could map it out. So we could map out non-Fermi liquid behavior. That help?
Yep.
Okay, good, thank you. Okay, so let's go on to field dependence. So these are some of my take home. I forget how long I have. So here's the magnetic evolution. So now we're not doing, the last couple were temperature dependencies. Now we're gonna sit at low temperature as much as we can, and we're gonna raise the field. Okay, now already we're starting from 2 kilogauss, right? By the way, every one of these junctions is always checked at low temperature to verify the quality. Do you have good quality single step elastic tunneling? So what we have on the left side is the 0, 0, 1 or C-axis direction. In that direction, HC2 is about 5 Tesla. This is a nice thing about being a magnet lab. You still have to apply for time, but we actually have 5 Tesla in my lab, but anyhow. This was done at one of the magnet lab, SCM1, I think it was. So here we are down at the lowest one here is 0.2. That's only the drive the lead normal. And we see a D wave gap. And now you crank up the field, and as you would expect, you start losing the gap. So if you look at 1 Tesla, it's weaker. 3 Tesla, by then you've wiped out the density of states peaks. 4 Tesla, 6 Tesla. Okay, by 6 Tesla, there's no more superconductivity in the problem. Yet we see this V-shaped structure. And the other interesting thing is it looks, and we have some plots we're going to kind of go into, that if we plot fitting these things, it's a very smooth evolution, which I think is an important argument. But we see the superconducting thing and smoothly goes into the splitting, right? Or which we call in the paper a gap-like feature that grows linearly with temperature. This is low temperature and it got this up to 18 Tesla. There's no superconductivity, anything above that green curve and above. If we look at the 100, where you have almost a 12 Tesla HC2, then we see the same thing. So we see at low temperature and low field, we see the superconducting gap. And as we start making up the Tesla, the gap starts washing out and this linear thing starts coming in. And so look at this thing, there's 11 Tesla, 14 Tesla and 18 Tesla. And we actually do see the same kind of thing in the 110 direction. And all splittings persist to the highest measured field of 18 Tesla. The ZBCP, zero bias conductance peak, decreases and splits with increasing field. And for the aficionados already at zero field, you have broken pairs, but we don't completely understand it, but we can tell that it's 110. Okay, now this is another key thing. Everything that is grayed out there, you've already seen. Okay, this is the field dependence at low temperature, well below TC, where we see the superconducting gap go into this linear region, this linear splitting region. What we have on the right here that's not grayed out is T above TC, not too high, Goldilocks, right? So not too high. So we see we're 4 degrees, 3 degrees, and 5 degrees. TC of this material is 2.3 degrees. So this is above TC. Okay, this is where everybody's saying there's precursors. And what do we see? We see some evidence that maybe there's something dipping in there, but we do see this linear splitting with increasing field. So what we see as a function of temperature, at low temperature and just above TC, up to twice TC, we see a linear growth of some gap or splitting field with applied field. Now the next thing, so we got, as long as we're below in the precursor or the superconducting state, we see the splitting, but let's go to a little higher temperature. So now we've done this at 10 degrees and 15 degrees. I wish we had more data. We're working on it now. But then you just don't see it. You see a little, if you look at here, this is a really small conductance change. It's flowing up here. But basically, you do not see that splitting. So if you're above the precursor, you don't see that splitting. Okay, these are just facts. We've done this a lot. We're doing it again other ways. Okay, so this is just plotting more things up. So this is just a magnetic evolution. This is just to show that we plotted it and that splitting is linear. It does smoothly go from gapping to this linear thing, and that's just verifying all that stuff that I was telling you already. I can send you these slides too.
I know, it goes in my notes so nicely.
Oh, very good. I've never learned how to write with that pen on the iPad. Sure, multi.
Question, maybe. Yeah, I think you mentioned this before, but I didn't quite catch it. So the lowest figures, they always show some kind of peak, which is then flat. The upper ones just show flat and then a dip in the middle. But they're all GP, aren't they? So what's different?
What do you mean GP? Okay, so Malte just asked, you see flat on the top and you see peak at the bottom. Okay, so this is not Andreev reflection. This is tunneling. Okay.
But are they showing the same quantity? That's what I'm wondering about. Like the vertical label is always GB.
Yes.
So are they showing some different measurements, or what's the orientation? It's literally depends strongly.
Yeah, and one of the things that I want to stress here is that they're shifted and we do some normalization, but if we don't normalize the data, we really get very reproducible conductance. So the y-axis is dV by di, right? The dynamic conductor, di by dV. I'm sorry, dyslexics of the world untie. So the y-axis is the conductance that we and we've gotten to a point, these are very, very reproducible. So the only difference between these, there's not a lot of playing around. These are pretty much raw data. They're shifted. And I think they're normalized. But if I showed you the unnormalized, you would be surprised. Even if they're normalized, look at the difference. They all go to 1.2, 1.4. The top two go from 0.8 to 1.4. That's really reproducible, even with different crystallographic orientations. Okay, so all that's different here is the orientation. And in both of these things, we see that this splitting or gap increases linearly with applied field. We also see it linear in the 110. We kind of think we understand it. It's gotta be an Andreev bound state because you can't get away from that. But there's so much condo stuff going on there, so that's like a big condo peak. It's hard to differentiate. Maybe we could use some.
Can you remind us what VP and VS are?
Okay, so VS is the superconducting gap, and VP is the linear splitting of the higher one. And we fit that, the superconducting gap is fit with BTK. And the higher one is fit to a curve, which we call, I think it's Frano, where you just fit it so you get, like, at a certain direction in, you get exactly what that gap width is.
I see.
So the black, that's VS, is the superconducting gap. The green, or VP, is the pseudo gap, or the preform pairs gap, or the.
And how does this compare with G mu B? B.
Oh, I forget, but I think it's too big again. I have that. So Pierce asked the question, how does that compare with G mu B? So if you want to get the G factor of these materials, you can plot this, and if you plot the conductance, the linear conductance versus bias, you can fit that, what is it? 2 delta versus B is G is, what is it? G is, what is it? G mu B times field. Right, okay. And sorry, I really have been doing policy the last 4 years. I need your help. And so that's a standard thing that you check. If you're tunneling into something, you expect this, it's higher than 2. I have the numbers. You expect the slope to be 2. An electron, the Bohr magneton is 2. And if you're tunneling, you should just measure the Bohr magneton of an electron. When you don't see that, something funny is going on.
Could it just be the G factor of the F electron?
It could be very anisotropic.
I don't know. I mean, one of the things in the high TC why we decided, anyhow, but yeah, we'll talk about it. Yeah, maybe those are interesting things to look at. Yeah, so we don't know. I know that when I was studying this years ago, that if you're tunneling into a magnetic semiconductor, you can get huge UVs.
Yeah.
So
too,
typically in a metal you don't, but this is
These are spin orbit coupled F electrons. So
yeah.
So they have much bigger G's than normal.
They're gonna have much bigger G's, and yeah, you're only measuring the electrons get through. I think that's a really good question, because now that you bring it up, what all you're measuring tunneling is what do the electrons look like when they get through. You're measuring resistance or conductance. That's all you're measuring, and it's what they feel like. Do they feel phonons? And if the F factor, if the Bohr magneton is the G factor, I'm sorry, you can't change the Bohr magneton, but if the G factor is different in different directions, that might be interesting. So again, hybridization is that the electron scatters off of the F electron and it picks it up and it feels it. And so we know there's hybridization here, and maybe that will help us differentiate. Okay. Yes?
Given the indications of the tendency to form preform pairs, is there evidence for a BCS BEC crossover?
The question was, given that there's evidence around that there's evidence for preform pairs in certain materials, and maybe there is here, is there evidence for BEC BCS crossover? Certainly the pairs are close here, and I don't know how to differentiate. So I think that I've been asked that, and I don't really know the answer, and I'm not quite sure how to get there. So I would value any input on how would we tell if it's BBC. We need the billion guys here to figure that out. Okay.
Oh, so can I ask? So you said you can't go too high up in temperature before you lose the pseudogap feature. So what's the temperature window, and do you have the pressure dependence of TC and the pseudogap temperature?
I don't have the pressure dependence. That paper that I will show you, flash you, did the pressure dependence in point contact spectroscopy, and they do have some pressure dependence. I'm still trying to understand it. So what we see here is that we see this precursor and we see this field dependence as long as this is an argument why we think it's preformed pairs, right? Because we only see this field dependence if either there's preformed pairs, if that's what they are, or Cooper pairs. I don't think that it's proved that it's preformed pairs, but it's interesting that you only see this linear field dependence of the splitting in the pseudogap phase and the superconducting phase.
So I thought you assume CeColn5, the neutron scattering have shown that in a particular field direction, you see this sort of FFLO phase, right? Which turns out not to be FFL. Do you actually see any features in that?
No, that's a different field and temperature dependence. That was the Q safe.
Yeah.
And that's what we started looking for. I have a slide that said we haven't really reached that area. No, we don't have any evidence for that. Yeah. So the question was, do you see the Q phase? My answer is, I have a slide on that. That's in a different field temperature area that we didn't get to. So, and we stopped looking because we saw this stuff. So, and I don't really believe it's FFLO anyhow. It's a couple of things.
So, Laura, just to clarify, when you explain the green curves, right, you said that these are the signatures of a pseudogap or preformed phase, whatever you want to call them. But as you see at high fields, that just goes linearly with field. Now I understand why Pierce was asking about the G factors. So what if you can't have the size of a pseudogap that grows with field? That's counterintuitive. So I would just measure the same of splitting of some advantages. Would you even call it a pseudogap?
So the question is, how could it be a pseudogap if this thing grows with field? These are just data. Okay, when I write any paper I've ever written, I never put my discussion in with the results. Okay, there's never I never have, I took my name off of the paper a couple of years ago when they insisted on using results in discussion. These are very hard measurements that take a lot of time and a lot of analysis and a lot of sample preparation. So the data, you can trust the data. The analysis, I change my mind on a weekly basis. So all we have here is that as a function of field, as we expect, the superconducting gap goes away in kind of a way we would expect. Also with field, we find the splitting that continues to a field that's way beyond the superconducting temperature, so it's not due to superconductivity, and it grows linearly. And Andre said, Zeeman, and that's why we reached into Pearson, Rebecca's paper. So this is something Shannon Rao, I had to study all this stuff. Rao was my postdoc advisor, and great guy. So this was a huge amount of stuff that was studied through the years, and we've all discussed these a lot, but basically, this is a tunnel junction. This isn't what I'm measuring, okay? What this is looking at a conventional tunnel junction. I forget what the materials are. It's tantalum and aluminum. So it's, aluminum is 1 degree, tantalum is 7 degrees, I forget, something like that. It's a little below niobium. So what they're looking at is an SIN junction, conventional. And these are the kind of things where tunneling was new, and they see these funny effects, and how do you explain it? So people had seen that what was going on in these materials, PTS is planar tunnel spectroscopy, is that they see this thing, that there's this big peak in the center, right? And as you apply a field, the peak splits. What's going on here? And so it was figured out by Anderson and Applebaum. By the way, Applebaum, in the early days, in the 60s, left Bell Labs to work on Wall Street. I bet he's a lot richer now. I don't know, but okay. So this is the Anderson-Applebaum theory that explains what happens when you have a magnetic impurity in a barrier or near the center of the barrier, at the edge of the barrier. And that's this right here. And so, yeah, how are we doing? So that's this right here. And so I'm just going to go over this because I think it's good for the students to learn about it. So assuming that you have
No, 20 minutes, including questions.
Okay, so I don't have that much longer,
Okay.
just another 6 hours.
Yeah.
So if you have simple elastic tunneling, and by the way, you can interrupt me, keep interrupting me, I like that. What we have there is a cartoon of conductance versus bias. That's what I've been showing you ad nauseum in this talk. So these are, you can calculate these things, but these are actually cartoons. So what we have on the top is we have, the top left is we have simple NIN tunneling. And what does that flat mean? It means you got Ohm's law. Okay, V equals IR. Okay, then if you do the same thing and you have some impurities in the barrier, you still get that Ohm's law until you apply a field. Why? And it turns out that when you apply a field, you get this peak. Sorry about this, if you're not all condo experts, but what happens is that when you have a tunneling electron going through and you have another electron that condo scatters in the barrier, they can interfere and they can give you a peak. Don't worry about that so much. Drop the peak stuff, but that's called the condo peak. And that's due to magnetic scattering in the barrier. What's interesting is the one on the right. So if you didn't understand that, you can understand this one, okay? So here on the right, on the upper right, it's still NIN tunneling and zero applied field. Now we're going to apply a field on the one on the right middle. So tunneling, unlike optical spectroscopy, if you have an impurity, you help the electron get through, right? Impurities increase the transparency. So if you have that's what inelastic tunneling is, and these things, you have something, okay, I don't have to tunnel all the way through this big barrier, I can hop on something in between. If you have a magnetic impurity in the barrier, if the electron has enough energy, it can scatter after that magnetic impurity and it'll help itself go through. So what we see here, that tunneling curve with the, I'm sorry, this one here. This tunneling curve here, okay? What we see here is that as a function of bias, at this bias here, finally, there's enough energy to help the electron through. It does a spin scattering and increases the transmission. So what we have is an excess conductance outside of, you have excess conductance as long as it's a high enough bias to flip the spin in the barrier. And since you're flipping the spin, that's going to grow linear with fields. Okay, so that's the Zeeman effect. So that's the Anderson-Applebaum, which says in an applied field, if you're scattering off of something magnetic, it will grow linearly with field. Now we have a big jump here, which is, this is where we have to figure this out. You see something linear in field and you think, Zeeman, right? And you think, could it have anything to do with this? So this is just some curve fitting to say that in the superconducting state, we can fit it, it's not surprising, the superconducting state, we can fit it to BTK and we see a gap evolving with field. And then with this function of field, we see this linear conductivity that reflects, we see this linear splitting, which reflects Anderson-Applebaum. Are they related? So here's the big jump. Okay. This is the Flint-Coleman thing, which is, frankly, this is a cartoon. So if you read their paper, and it's Nature Physics 2008, which Flint to zero, I'm sorry, I left Maxim's name off, I'm sorry. When I was talking, Flint to zero and Coleman. And there's also one on in 2010 and with Flint and Coleman. And so just the cartoon value, because I still don't understand all the calculations in there, is that what you have, if you look at the center one, okay, the idea from what I can understand in the paper is that it's a heavy fermion, you've got a condo doublet, you doubly degenerate. And so now you can have two electrons scatter after a single F level, right? And as you crank up the field, the F level is going to split linearly. Okay, is that I mean, I had some other back of the envelope calculations that were better. But, you know, it's just gonna split linearly, so the energy of these two electrons that were supposedly bound are gonna split linearly. If you go above TC or above the pseudo gap, you don't have this kind of two electrons scattering, you know, it's just, you don't have any pairing. So you don't have that effect. So that's the back of the envelope calculation, that's the guess. To go from a barrier scattering to an intrinsic, you know, scattering of the doubly degenerate F level is difficult, but I think there's a horsing in there somewhere. Okay, two other recent studies follow. So this is some great stuff, and there was a fantastic March meeting paper, and they've got a few papers out. They use this thing called shot noise. So we've been studying this like crazy in my group. Shot noise is noise due to the quantization of materials of electrons. And so there's this great argument that says measuring the shot noise will tell you if the electrons are grouped in 1E or 2E. And so that's one of the measurements we want to do. It has to do with androgen reflection, et cetera, et cetera. I'm not going to explain it here. It's a great paper. The person who gave the talk, I forget which person gave the talk. I think it was no, it wasn't. I forget. It was just fantastic at the March meeting. If it's online, it's really interesting stuff. By the way, there's another paper out that says no way shot noise can tell you if it's pairs or not. So it's all very interesting. And then there's this recent paper that I mentioned here, which is very convincing. And they argue that this pseudo gap has to be due to condo hybridization. And what they do is, I don't disagree with this. I've done this for years in the heavy fermions, which is that the background fits to a Fano line shape, right? And without going into all the detail here, but this background here that you see in the figure B, that's seen in every heavy fermion. That's due to the hybridization of the F electron to the conduction electron. And Fano, just to remind you, is something localized gaining itinerancy in the system. And depending on how they itinerant and how localized it is, gives you, it can be off center, the peak or the dip can be off center, it can be a peak or a dip, and it's definitely asymmetric, and the Fano factor tells you how asymmetric it is. So when we first published the Fano factor fitting, it was controversial because actually, you probably know the story, but you know, didn't you know about Harrison's theorem? Well, this isn't a Fermi liquid, okay? So we see this Fano background. We measure the same thing in tunneling and point contact that goes up to high temperature. They did something very interesting. So that inset there is supposed to be, I don't know, I'm not sure where they got that inset, but that's kind of a cartoon phase diagram. And I'm still trying to understand all this stuff because what they have here is their point contact spectroscopy. Look at the right one, you know, and they say that this pseudo gap as a function of pressure increases linearly. And they argue that because of the pressure diagram there, that's an explanation. I think it's probably not wrong. I think it's right, but I think both things can be true because these are complicated systems. Okay, so let's I'm gonna finish. Take a breath. Okay. Everybody and her sister agrees the x squared minus y squared now. There's something that exists up to about twice the TC. We have this increase in the magnetic field suppresses the gap, and a new splitting occurs well above HC2 that goes linearly with field. Smooth conductance field, et cetera, that it goes, the field evolution is smooth. There's no field induced gap or splitting at the higher temperature. Okay, here we go. I'm gonna have 7 here, and then I'm gonna have a slide where I'll just mention this again. The neutron spin resonance seen in the tunneling in the cuprate and iron-based superconductors is not seen. That's the 40 millielectron volt spin correlation peak. And we don't see that in the serum cobalt and 5. So this work, and basically they do see a peak at 0.6 millielectron volts, but no one sees it in the tunnel. So here's when we started talking about, could this be preformed pairs? Could this be F-level pairing? Everyone said, but D-wave means it's got to be spin-spin correlation. And I'm saying, no, it doesn't. You know, we don't know why it's paired. I mean, you know, the cuprates don't have F levels. Just, you know, so there's no reason to expect that it has to be the same pairing mechanism. So my last slide, local moments probably are involved, and what we're doing right now is we have 100 barrier materials, and we started the shot nose spectroscopy. That's it.
Great. Okay, we've got time for questions. Andre.
Laura, so as early in the talk, you did have one slide when there was a zero field, but then we quickly switched to where you made the lab normal and then look at SAS junctions. So when the field is zero and it's SAS, do you see Josephson? Do you see the two eta? And why is that?
It's hard to do that. To really do the Josephson junction, you have to take extra effort to be really low noise, etc. So we just don't see it. You have to have a smaller barrier. I rarely see that. It's hard. You have to have really higher transmissive junctions and make sure you're shielded from any outside field. And I have no shielding for Whitworth fields. So good question. Thank you. Oh, the question I answered why we don't see the Josephson current and zero bias because we're not good enough. Okay.
Yeah.
Go back to cuprates again, which is the only thing I know, but
They're not, it's not a self
there were
problem.
also pseudo gaps which might involve preformed pairs or might not. And I seem to remember the main one was the Nernst effect, which was seen as goes up to very high temperature, which was seen as evidence of some sort of pairing above TC. And I also remember some Andrea reflection experiments as well.
Yeah.
Not such a high temperature.
So the question is what's going on with cuprates as far as preformed pairs and Andrea deflection? Been there, done that. Yeah, so if you look at the phase diagrams that were popular then, when they would have the pseudo gap phase above the dome, the area where the group, I'll forget his name, but Ong's group, those of you that don't have your PhDs yet, get your PhD. I don't remember the first author. I remember my buddies and don't say his name. So like Meissner Aschenfeld effect, what the hell was Aschenfeld? Okay. So if you look at the pseudo gap phase, where it's been plotted out as preformed pairs is very close to TC. And then above is, So I think that's an important point. That's why I think everybody's right here. I'm a diplomat. Is that the pseudo gap phase we know is complex and it's not just one phase. The next one, Andrea reflection. Yeah, there was a lot of, I forget what you were asking, but yeah.
There was
So this is
Andrea reflection.
Yeah, so
Not so high.
this is still really
Still above
controversial.
Yeah.
This is a really great question, why I want to do the shot noise experiment. No one has ever answered the question, is can you, Andrea, reflect off of pairs that are not coherent? I don't believe that's ever been answered. And so it's a great question.
Very good. Okay, Penny.
But in your pseudo gap phase, I mean, would you think it's a pair without coherence, or you answer that, or you don't?
I think it's pairs without coherence, but I also know there's a lot of hybridization going on there. I don't think that point contact in Tucson Park's work is wrong. I just don't think you rule out that there's also preformed pairs. We have this funny thing was that they see this thing go up to very high temperature and there's not much happening at ambient pressure it's different measurements, they're complementary measurements. We see a real substantial change above 5 degrees. TC is 2.3, above 5 degrees, we see a difference.
The factor 2 is quite a lot.
Yeah, and so at they don't have much measured at the higher field. We'd like them to do that. I gotta give Tucson a call and.
It could be both, in fact, according to the Flint Coleman Davidovsky. It is.
Right.
Okay, yes, please.
So all of this is very dependent on the surface of cerium cobalt -5. Is there any evidence for surface reconstruction or any other changes at the surface?
So, so this is an STM, right?
Yeah.
So what I'm gonna tell you is that if there's some reconstruction, we're probably blind to it.
Yeah.
So we come down with a planar junction that compared to STM is a football field.
Mhm.
But we know what we're measuring. I mean, Seamus is an old friend of mine, and I don't know if we're talking anymore because. I don't.
Still
believe
here till
everything.
tomorrow, too.
Okay, good. But he, you know, he was always arguing all this high TC stuff, I can't get any reproducibility. And then when he learned how to do the scanning in QPI, if he added a bunch of things, he got what I saw. So I don't have that kind of resolution. I just sort of measured what electrons get through at kind of a certain momentum. So,
But from other work, is it known that there's surface reconstruction? At a sort of
She's saying it's not important, right? That's
Yeah.
what she's saying.
It's not a local probe.
Sorry?
It's a momentum space kind of thing.
But you don't know, you don't know in your measurements
No.
what's going on. I understand that. But are there sort of, for example, magnetic cerium atoms sitting on the surface, just as soon as you have a surface, and so -5? That's my question.
I mean, there probably are, I mean, we take pains to avoid that. But the fact that this change happens in 5 degrees. And you would expect this Anderson-Applebaum effect to last to very high temperature. Yeah, I think that's one of the concerns. That's one of the reasons we can say it's the Flynn-Coleman mechanism. And I think it's gonna be very difficult. What's really cool in one of these things is like I said, they go in from the side and they're measuring layer by layer. I have trouble with that because, hybridization, maybe when Seamus always at me, but hybridization is a bulk phenomenon. What does it mean to have hybridization at the surface, right? I don't know what that means. You have to be able to have the bands kind of, well, the lot of pictures of mouth they were showing, right? So I don't really know. And so if you want to argue that there's cerium in the surface and that's causing the splitting, that might be it. That's one of the reasons we want to look at different areas.
Yeah, sure.
Yeah, and. If that's the solution, then that's the solution. I'll be happy with it. I just don't know what the solution is, so.
I think it's a very good point to stop. Let's thank Laura. When do we reconvene this afternoon?
20 minutes behind, thank you.
Okay,
So I would suggest we reconvene 20 minutes after it said,
Which will be-
within 1.5 hours.
so, okay, I can't add, that means it's.
Sorry,
That means
10 to 3.
10 to 3.